Welcome to G Fun Facts Online. Today, we're talking about the junkyard in our own cosmic backyard. Low Earth orbit, the highway for our satellites, is now a celestial minefield. Millions of pieces of man-made junk, from dead satellites to tiny paint flecks, are hurtling around the planet at over 17,500 miles per hour. At that speed, even a marble-sized object becomes a ballistic missile. The question is no longer just how to get to space, but how to survive in it. And a big part of the answer lies in engineering a new generation of what can only be called space armor. The scale of this problem is staggering. The European Space Agency, or ESA, estimates there are over 500 objects larger than 10 centimeters, a million objects between 1 and 10 centimeters, and an incredible 130 million objects between just 1 millimeter and 1 centimeter. Traveling at these hypervelocities, an impact from something as small as a 1 centimeter aluminum sphere carries the energy of a hand grenade. This has led to the chilling theory known as the Kessler syndrome, proposed by NASA scientist Donald Kessler back in 1978. It's a cascading chain reaction. A collision creates more debris, which increases the odds of more collisions, which creates even more debris until certain orbits could become completely unusable for generations. Where does all this junk come from? It's the byproduct of nearly 70 years of space activity. We have inactive satellites that have run out of fuel, spent upper stages of rocket bodies left in orbit, and mission-related debris like lens caps and bolts that were just let go. But the most numerous and dangerous category is fragmentation debris, created from on-orbit explosions or collisions. Two events in particular added huge clouds of junk: a Chinese anti-satellite missile test in 2007 and the 2009 collision between a defunct Russian Cosmos satellite and an active Iridium communications satellite. So how do you protect against a threat moving at 7.5 kilometers per second? The first line of defense has been around for a while. It's called the Whipple Shield, named after astronomer Fred Whipple, who came up with the idea in the 1940s. The design is simple but brilliant. It's a thin outer bumper, usually made of aluminum, placed at a distance from the main wall of the spacecraft. When a piece of debris hits this bumper, the immense energy of the impact vaporizes both the projectile and a part of the bumper. This creates a cloud of smaller, dispersed particles. As this cloud travels towards the main wall, the impact energy is spread over a much larger area, drastically reducing its ability to penetrate the spacecraft. The International Space Station is a perfect example. Its habitable modules are protected by multiple layers of this shielding, often enhanced with intermediate layers of materials like Kevlar. But traditional Whipple shields have their limits. They're often heavy, and launch costs are calculated by the gram. Because they're metallic, they can create a lot of secondary debris when hit, which adds to the problem we're trying to solve. And crucially, they block radio frequency signals, meaning sensitive communication antennas can't be fully protected. This is where the new space armor comes in. A company called Atomic 6 has developed an innovative composite material that overcomes these limitations. Their space armor is the first orbital debris shield that is also RF-permeable. This is a huge leap forward, as it means sensitive communication gear can finally be protected without degrading performance. It's also fragmentation resistant, so it produces almost no secondary debris upon impact. Plus, it's lighter and thinner than traditional shields. They offer two versions. Space Armor Light can replace single aluminum panels and protect against impacts from particles up to 3 millimeters, which covers over 90% of the debris in low Earth orbit. Then there is Space Armor Max, which replaces the more robust multi-layer Whipple shields and can stop projectiles up to 12.5 millimeters. This quest for the ultimate space armor is driving a revolution in materials science. Researchers are exploring some truly futuristic concepts. For example, imagine a spacecraft that can heal itself after being hit. Scientists at Texas A&M University have developed a polymer with dynamic covalent bonds. When struck by a high-speed projectile, the material melts, allows the object to pass through while absorbing its energy, and then rapidly cools and reforms its bonds, effectively mending the hull in a fraction of a second. NASA is also working on multi-layered self-healing systems, where a reactive liquid monomer is sandwiched between solid panels. When punctured, the liquid flows into the hull and solidifies, sealing it. Then there are nanomaterials. At the smallest scales, materials show extraordinary properties. Carbon nanotubes, cylindrical molecules of carbon, are incredibly strong and are being embedded into polymers to enhance impact absorption. Graphene, a single layer of carbon atoms, is one of the strongest materials ever tested and also provides excellent radiation shielding. Boron nitride nanotubes are being explored for their ability to shield against neutron radiation. The future of space armor likely lies in advanced composites that combine the best of different materials. Think ceramic metal composites, or cermets, which blend the hardness of ceramics with the toughness of metals, or fiber-reinforced polymers using carbon, Kevlar, or Xylon. The most advanced designs will be multi-layered hybrid structures, with each layer performing a specific function: an outer bumper to break up the projectile, an intermediate layer of a self-healing polymer to absorb energy, and a back wall to stop any remaining fragments. But armor is only the last line of defense. A complete survival strategy requires being proactive. The most direct approach is active debris removal, or ADR, basically cleaning up our cosmic backyard. Companies and space agencies are developing a host of amazing technologies. There are concepts for deploying large nets to capture debris, or firing harpoons to snag junk for deorbiting. The ESA's Clear Space 1 mission plans to use a robotic arm to grab a piece of debris. A Japanese company, Astroscale, is pioneering the use of magnets to capture debris. There are even proposals to use lasers to gently nudge debris, altering its orbit so it eventually burns up in the atmosphere. For the millions of pieces we can't remove, the only defense is to dodge them. Collision avoidance is now a routine part of satellite operations. Space surveillance networks on the ground and in space track the larger junk. When the predicted paths of a satellite and a piece of debris get too close, an alert is issued. Satellite operators then analyze the risk, and if it's too high, they perform a maneuver. With the rise of mega constellations containing thousands of satellites, doing this manually is becoming impossible. This is where artificial intelligence comes in. AI and machine learning are being used to create automated collision avoidance systems. ESA's CREAM project, for example, aims to automate the entire process, from risk prediction to executing avoidance maneuvers, making space traffic management far more efficient. This isn't just a technical problem, it's an economic one. Protecting satellites costs money. Shielding and avoidance maneuvers can account for 5 to 10% of a total mission cost, but the cost of failure is far greater. A destroyed satellite can be worth hundreds of millions of dollars, not to mention the loss of the services it provides. The risk is now so high that satellite insurance premiums are skyrocketing. This economic risk is creating a business case for a cleaner space. A NASA study found that investing in debris protection could deliver economic benefits of over $50 billion over the next 3 decades. The market for space debris removal is projected to see exponential growth. We also face a legal void. The Foundational Outer Space Treaty of 1967 is from a different era. We have international guidelines on debris mitigation, but they are voluntary and not legally binding. There are no clear, enforceable rules of the road for space, which is a major hurdle to long-term sustainability. The proliferation of orbital debris is a clear and present danger to our future in space, and the solution must be as multifaceted as the problem. It requires a combination of next-generation space armor, using revolutionary materials, proactive strategies to clean up existing debris, and smart, AI-driven systems to avoid collisions. We also need a robust international legal framework to ensure all spacefaring nations act responsibly. As we look towards a future of mega-constellations, space tourism, and missions back to the Moon and on to Mars, securing the space environment has never been more urgent. By investing in these technologies, we aren't just protecting satellites. We are ensuring the final frontier remains a domain of opportunity for generations to come.